Hello again. In this video, we're going to go over an example where we use the net area function. Okay, so let's look at example 2. It says, consider the trapezoid bounded by the line f of t is equal to 2t plus 3 and the t-axis from t is equal to 2 to t is equal to x. Okay, so let's graph this function first of all. Notice that this function has an input variable of t, so that means this is going to be the t-axis. Then we're going to call the output variable y, so that's going to be the y-axis. And so if you graph this function, you're just going to get a straight line with a slope of 2 and a y-intercept of 3, so it's going to look something like this. And then let's find the net area function that has a left endpoint of 2. Then the right endpoint we're going to call a variable, we're going to call it x. We're going to allow the right endpoint to vary, so let's call it x. Okay, so then let's find the net area trapped between the function and the t-axis between these two endpoints. Well, that can be described with a definite integral. It's the definite integral from 2 to x of 2t plus 3. Now remember, this area function actually depends on the upper limit here, so it depends on x. It does not depend on t. That's because t is a dummy variable. The area trapped in here does not depend on the variable of integration. It actually depends on this upper limit, which we're calling x. Okay, so this area function that we've created, or net area function that we've created, actually depends on this right endpoint x. And that's because if we vary this, we get a different area in here. Okay, so let's find the area function, or the net area function, evaluated at 2. Well, if x is equal to 2, then there's no area trapped in here. Okay, so a of 2 should be 0. Okay, what about a of 5? All right, well, if x is equal to 5, then we need to find the area of this trapezoid. The area of a trapezoid is 1/2 the base of the trapezoid times the quantity h1 plus h2, where h1 is this height and h2 is this height. Okay, so the base of this trapezoid is just going to be 5 minus 2, so it's going to be 3. Height will be the y value when x is equal to 2 over here. And so if you plug a 2 into this function, you get 7 out. And so this has a height of 7 over here. So h1 is 7. And then the height over here, we can find by plugging a 5 into the function, and we get 13 out. So this should be 13 units high. And that's going to be our h2. Okay, so let's find the area using the trapezoid formula. So it's 1/2 the base times h1 plus h2, which we said was 7 plus 13. So here you would just get half of 20 would be 10, and 10 times 3 would give you 30. Okay, so a of 5 is equal to 30 in this case. Then remember, a of 2 was equal to 0. Okay, now let's find a of x. Okay, to find a of x, we're going to find the area trapped in here, again, using the formula for a trapezoid. Now we're going to think of this as some variable x. Okay, so the area of the trapezoid is still 1/2 the base times h1 plus h2. Okay, but what's the base in this case? Well, this distance down here is always going to be x minus 2, right, regardless of what x is. That's our base. This height over here is going to be 7, because when you plug a 2 in, you still get 7. So h1 is still 7. Then h2 is now going to be 2x plus 3, because now we're plugging an x in to get the height over here. Okay, so let's go ahead and plug that into the formula for the area of a trapezoid. So it's 1/2 the base. And remember, the base was x minus 2 times h1 plus h2, and h1 was 7, then h2 was 2x plus 3. Okay, and then we can simplify this. That's just 2x plus 10. And then I'm going to rearrange the order of multiplication because it doesn't matter what order you multiply in. And I'm going to put the 1/2 next to this and then distribute the 1/2, and that's going to give us an x plus 5 there, times x minus 2, and then let's just FOIL this out. So we get x squared plus 5x minus a 2x, and then plus or minus 10. Okay, and then if you simplify this, you just get x squared plus 3x minus 10. Okay, so we now have a formula for the net area that's trapped between the function and the t-axis with a left endpoint of 2 and a right endpoint that can vary, right, which we're calling x. Okay, so this is kind of a formula for that area. Right, you pick what the right endpoint is, or the upper limit here is, and you just plug it into here, and then this will give you the area that's trapped. So for example, we know that a of 5 is 30, right? So if you plug a 5 into this formula, notice that you do get 25 plus 15, which is 40, minus 10, you do get 30. The nice thing about having the formula is I can now just find it for any x value. Right, a of 6 or a of 7, I would just plug those numbers into here and get the area that's trapped, net area that's trapped. Okay, and then part D, what we're going to do is we're going to compare the derivative of the area function to the original function that we started with. And if you remember, the original function that we had was f of t was 2t plus 3. Okay, so let's compare those two. So let's find the derivative of the area function with respect to x, which, by the way, the area function is simply this definite integral. Okay, so let's find the derivative of the area function, and this is our area function, right? With respect to x, the derivative of this would just be 2x plus 3. Now, how does that compare our original function? Well, they're very similar. They're not quite the same. Original function depended on t, and this one we have a dependency on x. So it's not f of t, right? Because f of t is 2t plus 3, but it is f of x, right? So if you evaluate this function at x, you do get 2x plus 3. So that's what this is. So this is not f of t, it's actually f evaluated at x. So how does it compare to the original function? It's not the same as the original function, but if you evaluate the original function at this upper limit, which we're calling x, then you do get the same thing, right? You get 2x plus 3. Okay, so this gives us a very interesting result. Notice that when you take the derivative of this area function with respect to the same variable that we're using for this upper limit, in this case x, right? So when you take the derivative of this area function with respect to x, because that's our upper limit here, then what happens? Well, it seems like these two operations cancel out. And that's sort of what's going on here. You have a derivative, you have an integral. Those are inverse operations of each other. And so essentially these are canceling out. And that leaves you with this function here that you started with. Except this function, t was a dummy variable. It actually depends on the upper limit here, which is x. So that's why you get f of x and not f of t. So that's the way you need to think of this. When you take the derivative of an integral, they sort of are a definite integral, I guess. When you take the derivative of a definite integral, those are inverse operations of each other, so they sort of cancel out, and you're left with the original function. that function depends on the upper limit here. It does not depend on the dummy variable. Okay? Dummy variable, remember, for a definite integral, the dummy variable doesn't matter when you determine this definite integral. The thing that matters is this upper limit. Okay, and this is going to be one of the results that we see when we get to the fundamental theorem of calculus. This is sort of illustrating the idea that differentiation and integration are inverse operations of each other. Okay, and so that's why they're canceling out, and we're getting this original function here. Again, it's not a function of t, it's a function of this upper limit, which we're calling x. Okay, we'll talk more about the fundamental theorem of calculus in another video. For now, hopefully this one was helpful. Thank you for watching, though. Bye-bye.